So let's now review chapters 3 and 4. What are they about? What are those chapters about? You read chapter 3? Discrete distributions or discrete. I'm thinking of two words. One starts with the R and one starts with the V. Random variables. And we'll also talk about chapter 4 here, continuous random variables. So I'm going to sort of do them both chapters at once. How about that? So chapters 3 and 4, discrete and continuous random variables, RVs. Do them at once, and I think that'll be kind of nice because then we can compare and contrast them. We'll talk about the general theory here first, and then we'll get into some specific examples. And then we'll talk about using some Mathematica to do some simulation and that kind of thing. So maybe I'll have like two columns here, one for discrete and one for continuous. So we'll have the discrete stuff over here. Maybe different colors too, discrete and continuous. Okay, first of all, random variables, we treat them at a very intuitive level. There's a technical definition of a random variable that we never really get into. We just say a random variable is a quantity whose values vary according to some random model. Some for continuous probability density function, and for discrete, technically you should call it a probability mass function. Now again, I say our book calls both of them probability density functions, but I am going to always in this class, as long as I remember it, for a discrete one, call them probability mass functions. Okay, for discrete random variables. Actually, sometimes people shorten it to just probability function, but I'm going to call them probability mass functions for discrete random variables. And the key thing about discrete random variables is they take on values in either a finite set or what's called a countably infinite set, denumerable set. Either a finite set, 1, 2, 3, 4, 5, for example, or a countably infinite set, also called denumerable set. And what does that mean? It means it's an infinite set where you can list the numbers out in some order and essentially count them. Though to literally count them, you'd be counting forever. Like the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., forever and ever. That would be an example of a countably infinite set. There are uncountably infinite sets as well. There are different kinds of infinity, like the entire real number line, or even any open interval from, say, 0 to 1, for example. All the real numbers is uncountable. You can't list them in some order where you can literally count them. Now, you can list them in an order where you've got a number line, and you can say one is bigger than another, but you can't literally count them in some order. For example, there's no smallest positive real number. There's no smallest positive rational number as well, so that's not a proof of it, but that's a basic intuitive idea. Usually your countably infinite set is like 1, 2, 3, 4, 5, 6, etc., or 0, 1, 2, 3, 4, 5, 6, etc. Those are the most common examples of countable infinite sets that X could take on values from. And to find probabilities for such a random variable, you have a probability mass function or PMF for short, that says to find the probability that X takes on a specific value called little x. And in this class, I always need to try to make my little x a little cursive looking so that we distinguish between capital X and lowercase x. Capital X is your random variable, this abstract idea, this quantity that can vary according to some random model. Its values are determined by chance. Little x, you're thinking of being as just a particular real number. That is your probability mass function. I probably should have put that over there to the right. That's typically called little f of little x. I should have written the little f of little x first. Okay, but that is it. It's a function of little x that tells you how to find probabilities. And it often has a formula. Doesn't have to have a formula. Could be given just by tabular data in some table. That's actually the simplest kind of example, is you might have a table of values, for example. Maybe a little x can take on the values 2, 7.2, and 8.3. And the probability mass function values are maybe 0.4, 0.3, and 0.3. They do have to add up to 1. Yeah, that's a condition to be a probability mass function. The sum of all the values of the PMF has to be 1. Technically speaking, we also think of this thing as being defined for all real values of x. However, it's only positive on a finite set or a countably infinite set, where capital X takes on values with positive probability. But technically speaking, it's easiest to think of it as being defined for all real x, and wherever it's not positive, it's 0. And so technically speaking, if you want to graph this function in the technically correct way, here's 2, here's 7.2, and here's 8.3. You're graphing it at a discrete set of values where it's non-zero, and then everywhere else, technically speaking, it's 0. You should sort of consider the axis as part of the graph here. And these are supposed to be open circles there. That's hard to tell. Filled in the circles up here at 0.4 and 0.3 for these values here. 0 everywhere else. The probability mass function has a corresponding cumulative distribution function. CDF. Found by adding up, accumulating values from the PDF. Capital F of little x is the sum of the values of little f for all inputs up to and including little x. Technically speaking, I should use some other letter here for the input of little f here. Oh, how about a t? You could say for all t less than or equal to little x. This is technically defined for all real values of little x as well. However, we usually only compute it at those values of x where little f is positive. And yeah, we could make a table of values again for this example. Same example here of the CDF at x equals to 7.2 and 8.3. 0.4, and then 0.4 plus 0.3 is 0.7, and then 0.7 plus 0.3 is 1. But technically speaking, it's defined for all real x. It's going to have jump discontinuities at 2, 7.2, and 8.3 here. It's going to be 0 until x equals 2, when it jumps up to the value of little f at 2, which is 0.4. And then from 2 to 7.2, not including 7.2, it's going to stay at the value of 0.4. It's going to be a step function, it's called. Before, when x equals 7.2, then you actually do add on a positive probability and you get up to 0.7. And then finally, when you get to 8.3, you get up to a value of 1. That's technically what the graph of the CDF looks like. Technically, it is defined for all x. This technicality of being defined for all x is just convenient sometimes. It's not something you typically have to worry about too much. All right, let's compare now with the continuous case. If you're not quite finished drawing that, I will come back to it here, but we need to go back up to the top. Now you're saying x takes on values. I could say in an uncountably infinite set. However, that's usually not the typical way it's thought of. You usually say in a continuum. And what is a continuum? Well, essentially, it's an interval of real numbers, i.e., an interval of real numbers. Maybe the entire real number line, or maybe some smaller interval. Instead of a probability mass function, you have a probability density function. And again, our book calls them both probability density functions, but I don't think that's good. I will try to distinguish them. Probability density function, excuse me, still called little f of x, but unlike the discrete case, you don't find the values of little f do not give you probabilities. They give you probability densities. What does that mean? It means you have to integrate them to find probabilities. So I'll just write in f of x. I won't say it equals the probability that x equals x. Maybe I'll write little f of x gives probabilities by integration. In particular, the probability that x takes on a value between two numbers a and b. And it doesn't matter whether you make the inequalities strict or not. These probabilities all end up being equal in the continuous case. I'll go ahead and write them all. Those are all equal, and they equal the integral of the PDF from A to B. So the value of the PDF at any particular number doesn't give you a probability. It does have a value. For example, f of 2 could be 0.1 or something. But that's not telling you a probability. That's not saying the probability that x equals 2 is 0.1. It's saying what? Well, I guess I'm not completely matching these up here. It's saying if how should I write this? Let me say if delta x is small, if I've got a small number, positive number, it's going to be greater than 0. Small, how small? That depends. Depends on the nature of the PDF itself to some degree, how extreme its graph is. Then, well, the probability that x is between, say, a given number, little x, and a number a little bit bigger, little x plus delta x. Technically, that is the integral from x to x plus delta x of the PDF. And since I'm already using an x in the limits of integration, I should probably use some other letter now, like t. That probability is that integral, but that integral, if delta x is small, is approximately f of x times delta x, because delta x is small. That would be the area of a rectangle, an approximating rectangle for the area under the curve. And I'm just doing one rectangle. I'm not doing some sort of Riemann sum there. If delta x is really small, one rectangle might do a pretty good job of approximating the area under the curve. PDF might look like this. And by the way, the PDF doesn't have to be positive for all x. Maybe it's positive between here and here, and then it's 0 elsewhere. But I've got some number x and some small number delta x, so that x plus delta x is close to x. Then I'm saying, well, the area under the curve equals the probability of capital X being between little x and x plus delta x. But that area is approximated by this area of this rectangle, this skinny rectangle. It's analogous to having densities of like masses in physics. Like imagine a thin rod. And I'm saying a thin rod so that I can think of the mass density as being what's called a linear density, say grams per centimeter instead of grams per cubic centimeter. It's so thin, it's like one atom thick or something. I don't think you can make such a rod, but if its mass density near a point is like 2 grams per centimeter, and you cut out a little tiny chunk of it, maybe 1 millimeter long, 1/10 of a centimeter, really tiny. Its approximate mass would be the density, 2 grams per centimeter, times the number of centimeters, 0.1. So it'd be 0.2 grams, 2 times 0.1. That's kind of like what's going on, except we're not thinking about literal physical masses. We're thinking about probability masses. That product is the probability mass. The f of x itself is the probability density. How fast do probabilities get accumulated near the given value of x? The higher the graph is, the faster the probabilities get accumulated. But the value of f itself is not an actual probability. This does end up meaning the probability that a continuous random variable x takes on any particular value is 0. The probability that x equals a number a is the integral of f from a to a. There's no area under the curve, it's 0. How can that be? Doesn't x have to have some value when you observe it? Any bright ideas about how to, doesn't that seem like a paradox? How can you fix that paradox? A continuous random variable has zero probability of taking on any value, but it's got to take on some value. Any way to resolve that conundrum that you can think of? Think in terms of literal measurements and maybe even measurement error in experiments. I'm talking like science here. You're measuring a weight, a mass, or a length, or a volume. You're not going to measure it perfectly, right? When you say the mass of this thing is 5 grams, you don't literally mean it's exactly 5 grams. You mean it's 5 grams plus or minus some margin of error is what you really mean, because you could have made a mistake in measuring, or the scale is off a little bit. Nobody knows exactly what that mass weighs. And I mean, if we're talking about a continuous model, you might even say the exact value could be irrational for all you know. You might even wonder if that makes sense, though. 5.273946 blah 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 forever and ever grams. Okay, is that the exact number of grams? I don't even know if that question makes sense. But because you're really talking about measuring up to some margin of error, you're really talking about a probability of the mass being in a small interval, not an exact value. Does that solve the paradox? I think so, to some degree, though it still might feel confusing. You don't, except if it's discrete, you can count it. But if it's continuous, if it truly is a continuous variable for all practical purposes, you're not going to know its exact value, right? I don't know exactly how tall I am. Again, maybe it's not even a well-defined question, because, I got atoms at the top of my head that are falling off every so often or whatever, right? It may not even be a well-defined question. Even if they're not falling off, they're moving around. So, yeah. Analogous to the summation equaling 1 for the discrete case, what do we want over here for the continuous case? What's the analogy? So I'm not lining these up very well, but we still can separate them. Summation becomes?
Integrate from negative infinity to infinity of x.
Yeah, integrate to 1 over all x, which, since it's real, you can write a minus infinity into infinity. We want the integral for a PDF from minus infinity to infinity to equal 1. That's one condition for a valid PDF. I didn't mention the other condition in both cases. The other condition is your PDF in the continuous case has to be non-negative. You don't want negative probabilities. And that's the same thing in the discrete case back over here. It can take on 0 values for sure, but never negative. So it's always greater than or equal to 0. When I wrote the CDF back over here, I probably should have written something else as well on this line. I probably also should have emphasized that this thing here represents the probability that your random variable is less than or equal to the given little x. I should have done that, forgot to. That same effectively definition, this is really a definition. That equality right there is a definition. And the equality right there is more just, how do you compute it? That same definition holds for continuous as well. In the continuous case, you can say your CDF, capital F of x, is still the probability that capital X is less than or equal to the given little x. That is still the exact same formula as the discrete case by definition. But the way you compute it is different. You compute it as an integral instead of a sum from minus infinity to x. And once again, because I've got an x now in the upper limit of the integral, I should use some different letter here for the variable like t or something. It doesn't matter what you call it. T or u or w or v or whatever you want to call it. In the continuous case, what's the relationship between capital F and little f in the continuous case? Capital F is an integral of little f. Therefore, the derivative of fundamental theorem of calculus, in fact, says that the derivative of capital F is little f. For all values of x where little f is continuous, at least there, where little f is not continuous, like just some jump discontinuity like this picture, then capital F would not be differentiable at those values of x, at these two values of x here. Its graph, the graph of capital F would have like a corner in it. But at least where little f is continuous, here's my abbreviation for continuous, CNTS, that will be true. Capital F is an antiderivative of little f. Usually when you construct probability models, it's easier to think about the little f first, the PMF in the discrete case and the PDF in the continuous case. It's usually easier to think about those first, create those as your model, and then when you need to, you can compute the CDF. Though if little f is not a super nice function, even if it's continuous, you might have to approximate capital F by numerical integration instead of coming up with some formula, because the formula may not exist. It may be what's called a non-elementary function. And that happens, in fact, for example, for the normal distribution. Little f doesn't have what is called an elementary antiderivative, and therefore the formula for capital F is, well, it's unknown, you might say, though people have given it a name. In fact, they even have given it a special symbol when little f is a standard normal distribution. Little f, if x is standard normal, remember this? That means capital F is sometimes written this with a capital phi. Just a special notation that you'll see sometimes. Our book doesn't use it, but you'll see it some other times. Special notation for the CDF, cumulative distribution function of a standard normal random variable. Just letting you know, just in case you see it in some other book or some other online resource. I'm not going to emphasize that. What do we want to do with random variables? We want to use them as models. We want to find probabilities related to them and see if it matches reality. Probability is, I think, the pristine example of mathematical modeling that applies beyond just science, say, to, for example, business, social sciences. you're trying to create models that reflect reality. Sometimes those models make logical sense, like flipping a coin, counting the number of heads in 10 tosses, for example. It makes logical sense to use, remember, binomial distributions, binomial random variables in that case. Sometimes it's just purely based on data. You're an insurance company. You're wondering what's a good probability model for losses from fires for certain kinds of buildings in certain kinds of industries. Well, you got to look at historical data if you're going to have any idea of how to construct such a model. And maybe there's not a ton of data out there. And maybe the data that's out there is not very good. And so it's a lot of guesswork. You guess something and see how well it works in your business model. And then, you know, if it's not working, then you try to make adjustments. Maybe no standard kind of random variable is a good model. And so you got to make one up even. And what else do we do with random variables? We try to characterize them with summary statistics, you might say. Think you know what I'm getting at? Numerical statistics. Standard deviation and mean and variance. And if we got into things even more deeply, there's an idea of skewness and kurtosis. We won't get into that. Reflecting the nature of the distribution geometrically and summarizing the distributions, the PMF and the PDF especially, with single numbers. Yes, it gives a geometric meaning, but it also is useful for calculations as well. Once again, we have the discrete case and the continuous case. I'll try to do, I should have done these things more at the same time as I went. In general, you want the idea of a general expected value, expectation. I'll go ahead and call it, yeah, I'll call it general expectations. Or I'll just singular expectation. The expected value of some function of the random variable, call it h of x. Most commonly, h of x either equals x, giving you the mean, mu, or maybe x squared, giving you the, what was it called? If it's an x squared? Second, starts with an M. Moment. E of x is the first moment. The mean is the first moment. E of x squared is called the second moment, which is not the same as the variance, but is related to the variance. You could do a third moment, you could do a fourth moment. Those are related to skewness and kurtosis, and a fifth and sixth moment, and those are related to something. I don't even know what the names are. You could also do h of x equals x minus the mean quantity squared, and that would be the definition of the variance. Another common thing for h of x is e to the tx, where t is a real number. E to the tx. Remember what that was about? If that was an e to the tx there. Initials are MGF. Moment generating function. So there's lots of different things that h of x can be, infinitely many things h of x can be, but they're the most common ones. In the discrete case, that's the summation over all x, where the PMF is positive, though we could say all x, including where the PMF is 0 as well, and That'll be fine. Of h of x, oops, capital H of little x times little f of x. You do need to assume, in the case where it's a countably infinite set of where little f of x is positive, that this is what's called an absolutely convergent series, which means that if you sum the absolute values of h of x times f of x, that it converges. Now, f of x itself is never negative, so you don't need absolute value signs around the f of x. You'll see it in the book, what I'm talking about here. I'm not going to write it down. It's a technical requirement for this to exist. It may not exist. There are examples of PMFs and PDFs where the means or other moments don't exist because the corresponding infinite sum or improper integral diverges. That does happen. And they can even be valid probability models. All right, I'll do an example, not today probably, but maybe next Tuesday I'll do an example of that. Means and variances don't have to exist. They can be, in effect, infinite. Wouldn't think you'd want them to be infinite, but it could happen. And it could even be a valid model for some real life phenomenon. That's a capital H, by the way, and that's hard to see there. Yeah, then you have the variance of the random variable to be, well, by definition, it's this moment, this expectation, I should say, with this, where mu here is the first moment, the expected value of x. And then there's a theorem that gives you the computational formula for this that says it's the same as the second moment minus the square of the first moment. And then the standard deviation of x is the square root of the variance. And we call the standard deviation sigma, and that means we could also call the variance sigma squared. Is another symbol for the variance. I'm putting x as a subscript to emphasize the it's the variance, the standard deviation and variance of x. I guess I could have put a subscript on the mu as well. I will, I guess. You don't always bother with the subscripts. What about the continuous case? General expectation. The expected value of a function of the random variable x. Once again, h of x is most commonly x or x squared, or x minus mu squared, or e to the tx. But now you compute it differently. You compute it as an integral. And all x can be represented by minus infinity to infinity. H of x times the PDF. Back in the discrete case, that's a PMF. In the continuous case, this is a PDF. And once again, you need to assume the improper integral here is what's called absolutely convergent. So you need to assume that if I replace h of x with the absolute value of h, that I get a convergent integral. You might wonder, why isn't it good enough just to say this integral converges instead of putting the absolute value signs around the h of x function? And I won't go into details, but in a nutshell, it makes the summations and the integrals more well behaved. I won't say more than that. These formulas over here actually can just get carried over. They're the exact same formulas in the continuous case because they're just abstract formulas. Now we can talk about general stuff that applies to both the discrete and continuous case. In fact, I've already done that. These formulas here apply to both the discrete and continuous case. But let's continue with formulas that apply to both. Yeah, there's the moment generating function for a random variable x. M sub x of t, by definition, it's a weird definition, it's the expected value of e to the t x. Okay, I will separate how to compute that in both the discrete and continuous case. In the discrete case, that'll be a summation over all values of x of e to the t times little x times little f of little x, the PMF there. And in the continuous case, that'll be the integral from minus infinity to infinity of e to the tx little x times the PDF little f of little x, like that. By the way, not all random variables are discrete or continuous. Did you know that? I think I mentioned it in problem stats. I'm mentioning it now. There are some random variables that are neither. They are mixed, partially discrete and partially continuous. And they often have uses, and in fact, we will delve into those uses in this class, maybe even next week. They have uses in insurance, for example. To give you a little hint of a way such a random variable could come up, let X be the losses from fire in your building in the next year. Most likely there won't be a fire, so most likely X will be 0. There's a positive probability that X is 0. But if there is a fire, then you've got some losses, X will be positive, and the positive values of X would be better to model with a continuous model. It's discrete at X equals 0, a positive probability that X equals 0, that you have 0 losses from fire. But for positive values, you got to use a continuous model. You got to integrate to find probabilities. So there are mixed random variables, and we will, yes, delve into some examples, though we won't delve into the theory of them. What are moment generating functions good for? What do they do? It's in the name. They, yeah, find or generate moments. Huh? Yeah. Theorem. Yeah, actually, I should call it result instead of theorem, because I'm not going to state it as a theorem. Result, the kth moment of X is the kth derivative of the moment generating function with respect to its variable t evaluated at t equals 0. Or if you prefer, instead of that notation, you could put mx prime 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 dot 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 prime of 0, where there are k primes, right? K derivatives there. Of course, usually k is 1 or 2, but this works even if k is 3 or 4 or 5 or 6 or 7 or 8, blah, blah, blah. And this works whether X is discrete or continuous or mixed. Doesn't matter, it still works. Wait a minute, what? What in the world? What is this t anyway? You might wonder. When you define the moment generating function and compute it, during the computation, you think of t as fixed, but arbitrary. And then in the end, because t is fixed but arbitrary, your answer does depend on t. And so then you say, hey, that answer is a function of t. Now I'm going to think of t as a variable. And this is a function of t, and maybe it's a nice function. Maybe I can differentiate it and plug in 0 into that derivative. And yes, that's what you often can do, as long as it's defined and differentiable enough on some interval near 0. Actually, I've never tried looking into an example where x, the mean of x doesn't exist, and wondered what happened to its moment generating function. I think I want to do that after class today. I'm interested. I'm intrigued. Its moment generating function must not be differentiable at 0 if the mean of x doesn't exist. I will try an example after class. Not in class, we don't have time. You could try an example. Well, okay, I'd have to give you a hint about how to come up with an example where the mean doesn't exist, but I'll share it next Tuesday. I'll share the example I think of. What else is in chapters 3 and 4 in the general case? Not specific random variables here yet. Not talking about geometric binomial, Poisson, normal, exponential, gamma, chi-squared. Remember all those? Not talking about those yet. But what other general facts can you say? You can talk about properties of means and variances, for one thing. Expectation. Properties. For example, the expected value operator is linear. For example, I could write this. Maybe I should label this more properties. More properties. The book separates this into a couple properties. E of c times x, where c is a constant, is c times e of x. E of x plus y is e of x plus e of y. This one property captures both of those. The expected value operator is a linear operator. It's like a linear transformation in linear algebra even. But you might wonder, where are the vector spaces? Are the random variables elements of some vector space? So I'll let you think about that. There's also properties of variances. I'm including these in the same list here. The variance operator is not linear in the general case, but it does have nice properties. The variance of a constant times a random variable x is the square of the constant times the variance of x. You can factor the c out, but you got to square it if you do. You can say the variance of a sum is the sum of the variances, but only in a very special situation. If, what about x and y? You remember what goes there? Independent, yeah. But wait a minute. X and y are random variables. They're not events in some sample space. Tuesday, we talked about independent events. But these are random variables. How can they be independent? Well, in chapters 3 and 4, we take an intuitive approach. We just say they're unrelated. Knowing the value of one doesn't tell you anything about the value of the other. The definition of independent random variables comes in chapter 5, the multivariable chapter, which we're not doing today. This is true, but only if x and y are independent. I could even say this is an if and only if. IFF stands for if and only if. It's not an official word, but it's a math word. Shorthand for if and only if If this is true, X and Y are independent. If X and Y are independent, then this is true. Is that really anything on this? I think I better just stick with if. Okay. If this is true, then that's definitely true. I need to think about the other direction. Okay, you do need these things. This is not just theory for theory's sake. It is relevant, certainly for doing calculations up here, but also in a lot of problem solving and also in a lot of statistical models. This is applied statistics. We are mostly going to focus on statistics in this class, but we need the probability theory to do the statistics. As far as particular random variables go, I don't want to write stuff out because that's going to be too time consuming. But let me just remind you of some particular random variables, and then we'll use Mathematica to do some simulations to end class today. You should, on homework problems, be able to use what I'm about to show you. I'm going to just go look at the tables that you can use on exams in chapters 3 and 4 here. In probability and statistics, we mostly focused for the discrete case on geometric, binomial, and Poisson. Technically, Bernoulli is part of binomial when n is 1. In this class, we focus on those same ones. We use them whenever we might need them. Also, probably focus on uniform to some degree. This formula, 1 over n, is saying f of x equals 1 over n when x has these n finite values. The PMF is constant at those n values and 0 elsewhere. Same probability, 1 over n. If n is 10, this is a 1/10. Constant function at those values, but 0 elsewhere. It's a natural kind of distribution to think about. In the continuous case, its graph is a horizontal line above some finite interval. We'll talk about continuous uniform distributions as well, but this is the discrete case. So these are the PMF formulas. It's called the density here, but I'm going to call it a mass function, probability mass function. In the discrete case, you should be able to use those formulas to find probabilities. We will continue to skip hypergeometric and negative binomial. Okay, just for the sake of time. We don't have time to get into them. And they're not as relevant for our applications. If you didn't read the section about simulating a discrete random variable, I would highly recommend reading it if you did not. We will do some simulation next week beyond what we do today, and maybe even have some homework involving simulation. So read about it. It involves tables of random digits that you can also find in the back of the book. We'll probably use technology instead of a table, but you should understand the idea of what they do. In chapter 4, the particular distributions. This was page 78 for this table. Chapter 4, the table is late in the chapter, page 136, and it's sideways. In prob and stats, we talked about gamma, exponential, chi-squared, and normal. We'll do the same in this class whenever they seem relevant, and also do the uniform one. This formula is saying over the interval from a to b, the output of the function is 1 over b minus a, so that the area of the rectangle under the graph is 1. Gamma we don't typically use so explicitly most of the time, but exponential and chi-squared are actually both examples of gamma, you might remember. Exponential is the same as a gamma when alpha equals 1. And chi-squared is the same as gamma when alpha equals the thing called little gamma over 2, and beta equals 2. You compare these formulas. For their probability density functions, these truly are densities. There's the normal PDF with mean, mu, and standard deviation sigma. When you try to integrate such a thing, you have to use numerical integration, a table, technology. There's no simple formula for an antiderivative of this in terms of elementary functions. You can give it a name, but it's not a function you're used to from pre-calc and calc. Don't forget about the means and variances being over in this spot over here, as well as on the previous table. They depend on the parameters in fairly simple ways. That's nice. If people want to be actuaries, it is worth, for a uniform distribution, it is worth memorizing the mean and variance. The mean's pretty easy because it's just halfway between A and B. Variance is less easy to remember, but it is worth memorizing for exam P. For uniform. All right, let's spend our last 10 minutes doing some simulation in Mathematica. I'm not going to assign any simulation problems for next Tuesday, but probably for next Thursday there will be some. With Mathematica, we'll do also simulation in a spreadsheet next Tuesday. And I will start looking to see what kinds of things we can learn about R and whether it can do some basic simulations as well. So I'll put this on Moodle. But let me just show you some things. Just some simple examples of things you can do. You can use a built-in function called RandomInteger to simulate rolling a fair die. And I can give the output of that a name. I can call it, for example, roll. And it is best to use a colon equals here. If I just use an equals, it's not that it's wrong, it just doesn't work in an ideal way. I have to keep, well, yeah, it doesn't change as I continue trying to re-enter that. I'm just keep putting the cursor here and doing shift return, it doesn't change it. But if I change it to a colon equals, it's called a set delete operator. Don't worry about what that means other than every time I enter it now, it changes. That's more ideal. So it's following a discrete uniform distribution. The probability of x equaling 1 or 2 or 3 or 4 or 5 or 6 are all the same. They're all 1/6. So in the long run, about 1/6 of the time you get a 1, about 1/6 of the time you get a 2, etc. If you combine it with table and put a, for example, comma 100, you can roll 100 times. You might wonder, out of 100 rolls, what's 1/6 of 100? It's actually 16.6 repeating. There should be in the ballpark of 17 of each number. Not exactly, because it's a simulation, and because of randomness, the number doesn't match the exact probability. But you could use count. Like the number of ones, it should be close to 17 somewhere. Exactly 17. Do it again, it'll probably change. 22, not too far from 17. But it's 600 rolls and count the number of ones, it should be close to 100. Hey, exactly 100, how about that? That was lucky. Okay. If you modify it a little bit and use table combined with roll and a comma 2 there, you can effectively roll 2 dice at a time. and combine with table again, and you can do 100 rolls of 2 dice. You could total up the numbers on the dice. That's the total of 1 roll. When you add the numbers on 2 dice, it's got to be between 2 and 12, right? Though you're more likely with a sum of the numbers on the dice to be close to 7. You've experienced that before, right? Less likely to be close to 2 or 12. Can you simulate a loaded die, a non-fair die? Yeah, but it's kind of tricky. One way to do it is with something called a random choice. And this syntax will generate data where a 1 comes up with probability 0.1, a 2 comes up with probability 0.1, etc. A 5 comes up with probability 0.2, and a 6 comes up with probability 0.4. So most of these numbers are going to be 5s or 6s. And you can count them. Yeah, 5s or 6s total up to 62 of them out of 100. 1s, 2s, 3s, and 4s are the other ones. I wouldn't expect you to know that you could do this. I'm just showing you you can do it. And this is just going to give us the same output with a shorter line of code. Table generates lists in different ways. I'm not going to get into details. You can just mimic what I do here. If you like Mathematica, you might see if you can figure out how to program random choice using random real and maybe a function called if and which are logical functions in Mathematica. If you want to look up how to use those things, if you're interested but you just don't know what to do, and you've got some time to kill, and you want to look things up, you can look up, for example, how to use which and what it does. Point to the help menu in documentation to get that. I'm not going to explain what's in this section, but it's something related to something called the birthday problem. Did you know that if you've got 23 people in a room, 23 people, and you're wondering, what are the chances that there are 2 people with the same birthday? With 23 people in a room, it's about a 50-50 chance. Did you know that? Just 23 people. That should seem pretty amazing. There's a 50-50 chance that some pair of people have the same birthday. Doesn't mean there's a good chance you have the same birthday as somebody else, but that some pair of 2 people in the room have the same birthday. And once you get to a room with, say, 35 people, it's almost a guarantee. Even just 35 people, it's like a 95% chance that there's at least 2 people with the same birthday. I've done this experiment in bigger classes in the past where I had like classes of 35 people, and I said, okay, we're going to go around the room and you're going to each say your birthday. And if you hear your birthday called out, you should say, hey, that's my birthday. And I tried it, I don't know, like 10 times or so. And every single time there's been a match. Now that didn't have to happen, but it did happen. Every single time I did it in a room with 35 people, there was a match somewhere. So it's an interesting application of actually counting principles from chapter 1. So I don't want to go over it, but if you're interested. This section's got some continuous distributions in here. You can use Mathematica to like write the formula for a normal distribution. There it is. Hey, what's its antiderivative? What did I just say about it a few minutes ago? It's not an elementary function. Can Mathematica do it? Yeah, but its answer involves Earth. Earth? Earth's just a function you've never heard of unless you've been in a class where I've mentioned it. It stands for error function. That's why it's called Earth. It's related to errors in experiments, which is an example of an application of a normal distribution. What does this do? This evaluates that CDF. That's the CDF there. And by the way, I can plot it if I pick a particular value of mu and sigma at least. Oops. I pick mu to be 0 and sigma to be 1. There's the CDF. Well, not quite. Okay, sorry. I need to shift it up. It is an antiderivative, but it's not the CDF. I have to shift it up by 0.5 to get the CDF. That's the graph of the CDF of the normal, standard normal distribution. Mean 0 and standard deviation of 1. CDFs do have to be non-decreasing, going up or staying constant sometimes like they would for discrete. If you evaluate this at the mean, you got to get, well, okay, with ERF it's 0, but if you add a half, 0.5. Under a normal curve, half the area is to the left of the mean, or the peak is half the area is to the right. CDF, yep. If you use CDF, it involves ERF-C, and this is the literal CDF. ERF-C, whatever the C means, is enough to make this the CDF. If I plot this right away without adding a half, make an ERF-C and don't add a half. Oh no, wrong formula. Excuse me, there's a negative sign in front of the X and a plus sign in front of the mean. There it is. Mathematica can do moment generating functions. It can do gamma distribution, chi-squared, exponential, uniform. All right, we're about out of time. I wanted to also, I was hoping I would have time to use something called probability distribution in random variate. I don't have time for that, but what I will say in 10 seconds here is those are a couple commands I can use to simulate user-defined distributions. Not standard ones with names, but your very own pet distribution. You can use Mathematica to do simulation from that. That's pretty amazing. All right, I'll get the homework up by noon.